Okay, thank you very much. Thank you, organizer, yes, for organization this conference and invitation all of us. The title of my talk, Generalized Symmetries and Burgers Equation and Related Algebraic Structure. This my joint work with Dmitro Popovych and Alex Bilo, and also big influence on our work was made by discussion with Artur Sergeyev and Sergei Koval. So in fact, this narrow subject, this specific subject, specific example was considered in many textbook monographies and papers. In fact, it is one of the main illustrative example uh, on generalized symmetries, recursion operators, and other structures which are related to generalized symmetries in all textbooks. And I just collect textbooks where this example is really essentially used. In some monographies, some particular generalized symmetries of Burgers equation up to certain order computed, like in the book by Blumen and Kumei, or even for potential Burgers equation sometimes, like in this monography, the recursion operators related to Burgers equation are considered in Olver monography and Ibrahimov as well. So in Olver it is only one. It seems to me both are for the first time was considered in monography by Ibrahimov. Yeah, most advanced result are contained in monographies of Vinogradov with collaborators. Yeah. So this is last one. Yeah. So what they did, in fact, they prove that in each order the number of the generalized symmetry is finite. Yeah. Right. Wrote the leading term in each generalized symmetries. And in fact, if somebody could combine their result and results by Olver and Ibrahimov on recursion operator. So such combination could lead to the complete description of generalized symmetries of the Burgers equation. But it is not simple work still. And moreover, it is necessary to check all these results, which is also a piece of work. There is also papers devoted to the subject. So, of course, the first paper is the paper by Oliver, where he, in fact, introduced the notion of recursion operators. And again, the Burgers equation was the first example for demonstration of the theory. And then it was demonstrated for KdV equation, or de Vries equation. But in this paper, only one essential recursion operator of Burgers equation was presented. Yeah. There is also a series of papers by Sanders and Wong, and individually by Wong, devoted to so-called master symmetries. And again, Burgers equation is, in fact, first and main illustration example when they try to demonstrate efficiency of developed theory. Yeah, and in the paper by Sanders and Wong here, it even was somehow describes the entire algebra of generalized symmetries of Burgers equation, but the representation for elements of this algebra is very complicated, and in fact, it is not possible to use it this representation for proper conclusion, for studying structure of this algebra, etc. Our approach was somehow different from what was presented in the literature. It was to consider from very scratch the connection of Burgers equation to the linear heat equation, and then use this connection and knowledge on generalized symmetry algebra of the heat equation, and then produce required results for the Burgers equation. Yeah, so Well, if you start from the heat equation, so it is well known that it is connected with Burgers equation, but so-called transformation, but it is better to consider intermediate equation, so-called potential Burgers equation between these two equations. So if we make point substitution, in fact, it's better to write absolute value of u equal to exponent of w. Then if you satisfy heat equation, then W will satisfy so-called potential Burgers equation, which is already nonlinear. But of course, it is simple and can be, since it is linearized by point transformation. And if we differentiate this equation with respect to x and make substitution, which is quite simple, but it's already differential substitution here. And we will produce Burgers equation. What is the problem with the substitution differential? That since in contrast to the point transformation, which establish isomorphism between all symmetry structures and other structures like spaces of conservation laws and so on. So differential substitution makes some correspondence, but we should study which kind of correspondence we have in fact due to this differential substitution. And if we combine these two substitutions, so resulting substitution from the equation 1 to the equation 3, from the linear equation, heat equation to the Burgers equation, this famous Hopf transformation, but of course it is necessary to remark and always referee ask about it, that in fact this substitution was invented like, I don't know, 40 or 50 years before Hopf and Kohl, and was presented in the textbook famous on differential equations. Yeah, it's multi-volume. So what we have? We have such connections. So we have three equations. We have connection between them due to point transformation and differential substitution. And we will try to translate all results for the heat equation to Burgers equation. And here we use standard notation for symmetry analysis of differential equations. So we always will use total derivatives, but of course in different spaces of independent and dependent variables. So this is why we vary. Yeah? We have for linear heat equation, we have as dependent variable u. Here we have dependent variable w, and for last Burgers equation we have dependent variable v. And so, and of course, total derivative with respect to x we will consider as it is. But we always exclude derivatives with respect to t due to equations, yeah, and even total derivative operator, operator of total derivative with respect to t, we also consider on the manifold of equations. This is why we have only one derivative with respect to t, or all other derivatives with respect to x. So we exclude derivatives with respect to t and consider these operators on the manifold of corresponding equations, and also correspondingly all differential functions which we consider will depend only on tx and derivatives of corresponding dependent variables with respect to x. So the basic results here is the results on generalized symmetries of linear heat equation. This result somehow was known. It's mentioned in the handbook, CRC handbook on symmetry analysis of differential equation. But there is no proof in the literature about this results, and moreover no rigorous formulation. This is why we rederive this result. And then the algebra of generalized symmetries of the heat equation has very simple structure. Yeah? So of course, since it is a linear equation, so we have a path which correspond to linear superposition of solutions. So H is running through the solution set of this linear heat equation, L1. Yeah. And we have other part, which constituted by so-called linear generalized symmetries. Why linear? Because we have some linear differential operator here, it's P and G, generated by P and G, so it's some degrees, which acts on U, yes? And this why this differential function, which is characteristic, in fact, of the generalized symmetry, it depends linearly on derivatives of U, yes? And the basis of this algebra of linear generalized symmetries of linear heat equation is constituted by these operators Q, K, L, where K and L run the set of natural numbers starting from 0, so with 0. Important remark that, okay, now we can consider this as somehow recursion operators, yeah? So we can act on this, by these operators on our symmetries here, and these operators are related, in fact, to Lie symmetries of linear heat equation. So this P correspond to shifts with respect to X, which is trivial symmetry, and this is non-trivial Lilian transformation of the linear heat equation. And then, since this representation for generalized symmetries is very simple, so in fact, we can at once produce many results for the corresponding algebra. Of course, the interesting part of this algebra is constituted by linear generalized symmetries, and we can call this in analogy with essential Lie invariant algebra. We can call this as essential algebra of generalized symmetries. And since representation is very simple, so we can find commutation relation for this algebra and also compute with infinite dimensional part and also study its algebraic structure. I will mention about this later, but now I will say that in fact this algebra is isomorphic to the Lie algebra associated with the first Weil algebra. So it's very famous algebra related to ordinary differential operators with polynomial coefficients. And then we also, due to this, we can produce a number of results on the structure. Okay, but yeah, what about second term of in this sequence? Since we have here point transformation, so and we can just transform all results for the linear heat equation to results for the potential Burgers equation. And so the algebra, in fact, is isomorphic. Of course, vector field would be modified a bit, but this is still not the problem. The structure of the algebra is the same. So we still have the Lie algebra associated with the first Weil algebra. Yeah. But what about the second tradition? When we will make transition from the potential Burgers equation to the Burgers equation via this differential substitution. How we can make this transition? So we should take generalized symmetry vector fields of this equation to Burgers equation, potential Burgers equation, and then prolong them to derivative Wx. And then if it is possible to project these vector fields to from the space with W to the space without. So it should exclude W. And then we should replace Wx by this expression for V in view of this substitution. It appears that this process lead to well-defined homomorphism. I will denote it phi from essential part of generalized symmetry algebra of the potential Burgers equation to the algebra of generalized symmetry, entire algebra of generalized symmetries of the Burgers equation. Yeah? So what procedure we have? So it's analogy of this operator GNP for heat equation, yeah, the images. So we have such generalized symmetries for potential Burgers equation. We prolong it, yeah. Then we cut this part, and then rewrite this part in terms of this variable. So we replace Wx by this. And a result, we produce these operators Q hat, which have this form. where operators P and G somehow images of operators P and G for the heat equation. Yeah, I will show them. Yeah, so this operator. So in fact, it's somehow mapping this operator for the Burgess equation. So we have this homomorphism, and its kernel is spanned by this most trivial symmetry Q tilde 0, 0, and for this symmetry, in fact, it will be just dw, so it will be equal to 1. So we have known this part. And so we denote image of this homomorphism by lambda 3. So in fact, we have that this image constituted by such vector field. So in fact, we also can attach to this 0, yeah, but in Q hat 0, 0 just equal to 0. Yeah, we will use also this later. And so this lambda 3 should definitely contain in the algebra of generalized symmetry of the Burgess equation. But if we make computation, yet here we make this computation, in fact, we show that lambda 3 coincide with sigma 3. So entire algebra of generalized symmetry of the Burgess equation is the image of this homomorphism phi. But to do this, we in fact should make some computation of generalized symmetries for Burgess equation in contrast to potential Burgess equation, where it was sufficient to use just a connection between linear heat equation and potential Burgess equation. In this computation, we make trick, yeah, because if we consider this jet space, so space of independent variables and derivatives, so all computations are very difficult in these variables. If you don't believe this, so you can look in the textbook by Vinogradov and company. Yeah? But we can switch from this system of coordinate system to the coordinate system with zeta k, yeah, where coordinate zeta k just action of this operator p on 1. So it is some polynomials in derivatives of e very specific. You see here like first two of these polynomials. And in fact, yeah, there is one-to-one transition from this coordinate to this and back, yeah. And why it simplifies all computation? Because we have very simple action of this operator, else operator dx, yeah, on zeta k, yeah. And especially when we will write generalized invariance conditions, it's just a linearization for Burgess equation, yeah. So this is condition in total derivatives. Since we already consider total derivatives in manifold, we should not take it into account as manifold of our equation, yeah. And if we expand this, so we will have just this. So we have all this coordinates zeta k, in fact, explicitly without big sums, binomial coefficients, and so on. And this strongly simplify all computation. And then usual standard trick that we restrict order of derivatives, check for number of independent generalized symmetries with such order, and then we show that in fact this generalized symmetries exhaust all such symmetries up to certain order of this form. Okay, so we prove that we have such algebra generalized symmetry. What are consequences from this we have? The first consequence, in fact, about the form of the symmetries, because since the form of the symmetries were not known so explicit, yes, it is written here, yes, it is just this expression, yeah. Then even this result, I don't know where it was presented somewhere, but it is important if we try to discuss action of recursion operators on generalized symmetry. So it's clearly, of course, visible from this form of generalized symmetry that all characteristics of the generalized symmetries belong to the image of the total derivatives with respect to x. Yeah. Then we also can characterize them as structure. Yeah, and function of jet variables. So each characteristic of these symmetries of which we consider of order R is a polynomial with respect to jet variables up to this order. Yeah, it is affine with respect to highest order derivative. Yeah, and coefficient of this highest order derivative is polynomial with respect to t only, and degree of this polynomial is not greater than R. And total degree of this characteristic with respect to x is not greater than R as well. Okay, so for example, such kind of results are presented, for example, in textbook by Vinogradov and company, two textbooks, but they were derived via quite complicated proofs. What about algebraic structure? So we already say that our algebra of generalized symmetries of Burgers equation is isomorphic to the algebra of essential algebra of generalized symmetries of the potential Burgers equation, and this algebra is isomorphic to the algebra of linear generalized symmetries of the heat equation, and both this algebra then isomorphic to the Weyl algebra, to the Lie algebra associated with the first Weyl algebra of real numbers. That's why I indicated them here, real numbers. Okay, since the kernel of our homomorphism is one-dimensional, it constituted this symmetry. So this is why the algebra of generalized symmetry of the Burgers equation will be isomorphic to the quotient algebra of this Lie algebra, which are associated with the first Weyl algebra with respect to its center, which constituted by trivial element 1, scalar element 1. Then we describe, in fact, algebraic structure of our algebra of generalized symmetries. Yeah. And then what we can say about this? We know that this algebra is simple, so, and then this algebra also will be simple. Recently, we proved with Sergei Koval that the first Weyl algebra, Lie algebra over which are associated with the first Weyl algebra, is two generated, and this then, in fact, quotient algebra is also two generated, and then algebra sigma 3 is also two generated. So what means two generation? This means that if you take two elements of the algebra and make with these two elements all allowed operations. So what this means? We can take Lie brackets, successively brackets here, and make linear combinations of these results. And in this way, in fact, we can produce the entire algebra of general symmetries of the Burgers equation. And here I presented examples of such two elements. But of course, we can say even a bit more, but maybe it will be already some talks in the future about this. Previously known results was that only that it's results again by Vinogradov, Krasильщик, and Arlichagin, and it was known that the algebra of generalized symmetries of the Burgers equations is generated at most 3 symmetries. So in fact, we lower this number, yeah, and 2 is in fact minimum, absolutely necessary minimum for such generation. Then, of course, due to this homomorphism, and since we know that it's kernel, we can easily write commutation relation for this algebra. And since you see we have quite complicated elements, so it is almost impossible to compute commutate Lie brackets of such vector fields directly. Yeah. So in fact, we computed them for heat equations that then transfer them to the potential heat equation, commutation relation for generalized symmetries of the potential heat Burgers equation, and then we can again translate them to the commutation relation for the Burgers equation. Yeah? Direct computation, as I said already, direct computation of this commutation relation is almost impossible. In particular, for specific element Q11, yeah, which is in fact just we have here 1 and 1, and this corresponds to the scaling operator. In terms of Lie symmetry, yeah, we have the following commutation relation. So this means that this operator is diagonal in the standard basis of this algebra, yes. And this also means that is diagonal inner derivation in this basis, yeah. And this is why these subspaces, which correspond to fixed eigenvalues, which are int components of some z grading of this algebra. Yeah, so we can represent our algebra as a direct sum of such subspaces gamma m, and this subspaces commute in this way, and this is why it is a grading of our algebra. So this is somehow again consequence of established homomorphism and knowing structure, algebraic structures that all this related to the first Wild algebra. Of course, then we also can easily write subspaces of generalized symmetries up to certain order. Yes, so we just restrict. We know that this symmetry has order A plus L, and so if we will introduce this restriction, we will describe spaces of corresponding order. Moreover, if we take higher order generalized symmetry, so in their linear combination, we cannot, how to say, so higher order term cannot be cancelled via linear combination. Yeah, this is why and we can then we know then dimension of these subspaces of generalized symmetries for finite order. If we recall about Lie symmetries of Burgers equation, so we have 5-dimensional algebra. Yes, and these basis elements of this algebra, this shifts with respect to t, scaling operator, this is conformal transformation, Galilean transformation, and shifts, they are related to elements of our algebra in this way. Yeah, so this is in fact elements of order 2, they are related, and these elements to elements of order 1. Yeah, and if we consider subspaces of the elements of the first order, so, and subspace of elements which whose order is not higher than 2, or even we can consider subspace elements of only of order 2. So all of them constitute subalgebras in this algebra, in the entire algebra of generalized symmetries, because these subspaces are close with respect to the corresponding Lie bracket. But these subalgebras are very specific because we prove that subalgebra of the generalized symmetries of order 1 is only this is the only finite dimensional maximal abelian subalgebra in the entire algebra of generalized symmetries. And we have also conjectures that the algebra sigma 3-2 is the only finite dimensional maximal subalgebra sigma 3, so including non-commutative. Yeah? Why it is interesting and important? Because in context of Wile algebras, of even first Wile algebra, there is some studies on its maximal abelian subalgebras, and in fact, it was initiated by Dixmier in 1968. Yeah, and in particular, he proved that any maximal abelian subalgebra in the first Wile algebra coincide with a centralizer of an element of this algebra, a non-scalar, and this element, of course, necessarily contained in some in this algebra. So we can say that this maximal abelian subalgebra coincide with non-scalar element of this algebra. Yeah, and that's why we can also translate many of these results to maximal abelian subalgebras to the algebra of generalized symmetries of Burgers equation. But of course, here very specific that this algebra is not first Weil algebra, but this factor algebra. Yeah? So we have isomorphism. This is why, for example, here appears finite dimensional maximal abelian subalgebras. But all other maximal abelian subalgebra in sigma 3, yeah, they're necessarily infinite dimensional and contain subalgebras of such form, yeah, in fact related to degrees of some constant polynomial of our this operators p hat and g hat in terms of which we express our elements q, k, l. And we also can guarantee that this maximal abelian subalgebra each coincide with centralizer of an element from the complement to the algebra sigma 3, 1. Yeah, and then such element necessarily belong it, and then we can take some element in its relative complement. In fact, any element in its relative complement. So centralizers of some maximal abelian subalgebra, yeah, which lay in relative complement to this, they coincide, and this is entire algebra itself. Okay, then the last discussion is about recursion operators. For Burgers equation. So for linear equation, we can restrict ourselves with standard differential operators, but for nonlinear equations, it's quite common that we should consider pseudo differential operator. And then we have some kind of inverse of total derivatives operator, and then it is necessary to interpret this. In informal approach, we just consider it as formal inverse to the operator dx. Of course, this is not in case in non-formal approach, yeah. But still, if we consider such two operators, so this well-known recursion operators for the Burgers equation, but in fact, using this description of generalized symmetries, we can prove that even within the formal, always formal approach, yeah, these two recursion operators suffices to generate the this entire basis of algebra sigma 3, which we presented, yeah. And as seed symmetries, it suffices to take this Q01 and Q hat 1, 0, yeah, and X on the symmetry, and in this way we will produce entire algebra of the Burgers equation, basis of this algebra. But of course, a basis. But of course, since we have such relations, so this means that we have not unique way for deriving, for representing the standard basis in the term of recursion operators. But for such elements with zero L number or K0 number, so representation is unique. But for all others, yeah, recursion operators, so we have multiple representations in this approach. But in fact, more justified is approach with when we interpret recursion operator as Backlund transformation for linearization of the corresponding system of differential equations. So if we consider generalized symmetries of Burgers equation, yeah, so in fact the condition for the generalized symmetry is the linearization of the Burgers equation, as I mentioned already. And this equation takes this form, yeah, and we can write this equation in the conserved form. And due to this form, we can introduce potential theta. Yeah, so in fact, it is, yeah, we can exclude it by cross differentiation. Yeah, this left-hand side, then we produce this equation. Okay, and then such defined potential theta by this system. Of course, it is defined up to arbitrary constant summon, and it can be considered as a proper value for the action of this operator dx minus 1, so inverse to the total derivative with respect to x on theta, on eta. And if we exclude eta from this system, we will produce single equation for var theta, and this equation is in fact linearization for the potential Burgers equation. So in fact, theta is generalized somehow symmetry for the potential Burgers equation after, of course, again, this substitution, yeah? And then we can show that action of recursion operators on eta, in fact, is coincide with action of some differential operators on theta. Yeah, so we have pseudo differential recursion operators. Yeah, we have d minus 1 in this recursion operator, but using tricks transition to potential, yeah, we can present as the action of some differential operators on theta, and then this action is well defined, and moreover, in this framework, it suffices to take zero seed symmetry, yeah? And if we will act by this recursion operator already as Backlund transformation, so we can produce first order symmetry first, and then we can produce the entire tree of symmetries. So this is why, of course, this approach preferable, but somehow the first approach, formal approach, is more native, yeah, in some way. And the very last point is about generation solutions of the Burgers equation using generalized symmetries. So in fact, we cannot use generalized symmetries to generate new solutions of some nonlinear differential equations from its known solution. But due to the Burgers equation is a linearizable equation, or it's also called C-integrable, and using generation of solution for linear heat equation by generalized symmetries, yeah, we can show, we can derive some formulas for such generation for the Burgers equation, and they take the following form, but unfortunately here it is necessary to write, so Q hat is here any generalized symmetry, linear generalized symmetries of the Burgers equation. So, and this is why the characteristic has this form. And in this way, action of operator dx minus 1 is well defined. So for this, we need to know that characteristic of any generalized symmetry of the Burgers equation belongs to the image of the operator of total derivative with respect to x, yeah? Or we can write this formula directly in the term of polynomials of these nonlinear operators in V, yes? And this very particular cases of this formula were known in the literature, and we know Professor Tichin from our school. He worked on this generation formula for a long time, and together with collaborators, he presented such formulas for such generation formulas for such particular cases, 3 particular cases in some paper, which was published in the C. Okay, so thank you very much for attention.
Thank you so much, Professor.